Hello everybody. So 6 years ago, I created a video called Cool Graphs Display, and this is going to be Cool Graphs Display number 2. I was like 19 then, and I had a bunch of graphs I had made using Desmos, and now I have even more graphs that I've made using Desmos, so let's get right into it. So here is an idea that I got off Mythologer, watching his videos. They're pretty cool. And basically, let's start with a simple example. M is equal to 2, and N, big N, is equal to 10. So what we have here is 10 points. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And what you do, this is the procedure for drawing the graph, is you start at a point, let's say 1, and you say, okay, what is 1 times little m? So 1 times little m is 2. Modulo 10 is still 2. So we draw a line from 1 to 2. And we can do the same operation with 2. What is 2 times 2? Modulo 10, it's 4. So we draw a line from 2 to 4. And we can do the same thing for that. What is 4 times 4? Oh, sorry, 4 times little m, 2, is 8. Modulo 10 is still 8. So we go over here. What is, here's another example where it gets bigger than 10. So we have 8 times 2 is 16. Modulo 10 is 6. So we draw a line from 8 to 6. And that's how we get this graph, or whatever you call it. Yeah. And let's pump up 10 to 200. And as you can see, we get this curve here is actually a famous curve called the cardioid, and we get a bunch of cool shapes. Every time we increase m, we get more different cool shapes. Look at that. And look at that. Wow. What? You wouldn't expect to see all this order. Maybe you would. Modulo times tables. And this is from a Mythologer video. And what we can do is, instead of making the step 1, we'll make it nothing, and then we will play it forward, and we'll slow down that play speed. We get all these different cool graphs. Pretty great. You can hear my fan going. In fact, maybe my mic's too close to my fan, but deal with it. So there's that one. This one's a bit advanced. It's called wave packets. I mean, the equations are not too complicated, but basically what this is this red function here. It is the frequency domain of the blue function, okay? And therefore the red function is the, I already said that, it's a frequency domain of the blue function. The blue function is the time domain. Yeah, you know what, I'll just demonstrate. So let's say f is equal to 8. So that's the mean of this red function. And a is like the standard deviation, sort of like how tight it is. And basically this is a demonstration of like Heisenberg's uncertainty principle, which says that the more you know about the position, the less you know about the frequency, which in quantum mechanics is the momentum. So if you're very precise about the frequency, you know very little about the position. But if you are less precise about the frequency, you can be more certain of the position. As in, see how this wave packet bulges into a more precise position. And we can play with the frequency, so if we can turn up the frequency, it's now a high frequency wave packet. That's right. And if we are more precise about the frequency, we know less about the position, and if we are less precise with the frequency, we know more about the position. So that's basically wave packets. Kind of cool. You basically just add up like a Gaussian amount of each sine wave. We have 40 in this case. So that's that. Gaussian blur. This is like a kernel convolution. Kind of hard to exactly describe, but it's basically an operation you can do on the red function to turn it into the blue function, which is a blurred version of the red function. In order to blur a function, you kind of get a section of that function and do a sort of moving average on it. You kind of sum up all of the surrounding values, and the closer those points are in proximity, the more influence they should have over the average. So basically you get this function, which is a Gaussian, this blue function, this little one, blue here, and maybe I should make it a different color. I don't know how to do that. And basically what you're going to do is you're going to place this at a certain point in your function. Like let's say we put it at 2, at x equals 2. So put the mean of this blue function over here, and then integrate over the interval of that function, which is from here to here. So from here to here, add up all of the values of the red function times the Gaussian, and output the result. And we should expect to get 0 here because we have just as much red on the bottom as we do at the top. But if we look at a point here, obviously there's more red above than there is below surrounding that point, so it looks like that. And we can change the width of this Gaussian thing, and then it has to integrate over a bigger area, and it's a more blurred out version of the same thing, which is the red sawtooth function. So there is that. We could do something where I swap this out, K with S. So now, instead of blurring this one, we're blurring the floor function. Let's get rid of the blur. So here's the floor function. It looks like a bunch of steps, but when we blur that, it looks like this. Blurred steps. We can increase A, and they're more and more blurred. So that's how Gaussian blur works, somewhat. Interpolation, sort of just like an improved version of a video. I mean, something I already talked about in the last video 6 years ago. But basically the idea is that you can get any trinomial, any third degree polynomial, and make it go from one point to another point with any given slope at the first point and any given slope at the second point. So this is how you might do. It's called bicubic interpolation, I think. I just called it my interpolation. So we have that. Projectile motion, I've already showed that in the last video. Fourier. This one's a bit nasty and complicated, but basically I'm doing a Fourier series which approximates the function f on the interval -pi to +pi. And in this case we're approximating it using 7 sinusoids of cos and 7 sinusoids of sine. That way we can get the phase right, because you have to use cos and sine to get the phase right. I'll get into that later a little bit. But basically, as you can see, it's the sum of 7 values, 7 cosines of varying frequency from 1 to 7. And how much of each cosine do you need? Well, the way you figure that out is you integrate here, say from -pi to +pi, f of x times the cos function of a certain frequency n, and see how many times see how much they correlate well with each other. So how much of that cosine frequency do you want in the output, and then you multiply that integral, which is how much of that cosine is in there, by that cosine. And you do the same thing with sine. Add them all together and you get the blue function. So this is pretty unfascinating because this is a sawtooth, and I already know how to do a sawtooth. But what if we used e to the x? Now this is going to be a bit slow for my computer. but I'll blame it on Desmos. I believe it could be done faster, but it's a web app, so give it a second. But it's going to approximate e to the x on the interval from negative pi to positive pi, that blue function there. So see, we have e to the x, the red one, and by adding together 7 sinusoids of cosine and sine, we're able to sort of approximate that shape, but it's periodic because we're adding a finite amount of sinusoids. Allegedly, you should be able to get it non-periodic by adding an infinite amount, but turning this number up to infinity would mean the program would never run. So there's that. You can only do a finite amount of work on a computer. What do you know? This is a visualization of an electric field. This is a positively charged particle. This is a negatively charged particle. And the length of those lines is proportional to the strength of the electric field at those points in space. So we can sort of get a visualization of the electric field. Maybe show that to some high school students. So that's pretty neat. This one, I don't know what I was thinking. I don't know why I made that. I probably needed it for something. Maybe a program I was writing. This one, it gets pretty involved. It's kind of hard to describe, but basically I was trying to answer the question, how far do you have to drop something from the surface of the Earth, neglecting air resistance, for its speed to reach a given speed by the time it hits the ground. So what this would suggest is that in order to get an object moving at 20 meters per second, you have to drop it 20 meters off the surface of the Earth, and in order to get it moving at 40 meters per second, you should drop it at 80 meters, from 80 meters. Anyway, if you take a look at this, this is the actual true function, this blue one. Take a look at it. It looks almost exactly like a parabola. And it pretty much is exactly like a parabola. As you can see, this is a parabola scaled by a factor of 20. And yeah, it looks pretty much like a parabola, but it's not a parabola because, you know, if you wanted to achieve like a very high speed, you could achieve that with a parabola. Anyway, I won't. Maybe I'll say it this way. The Earth has a force of gravity towards it, depending on where you are. If you're close to it, it's greater. If you're farther, it's less. But it's never zero, as in all objects in the universe have a non-zero gravitational attraction towards the Earth. But that may lead you to believe that if you were to fire something away from the Earth, since it's always getting pulled on by the Earth, it will eventually come back to Earth, neglecting the expansion of the universe. But you might think that, but it's not true actually, because even though it's always getting pulled towards the Earth, it's so little when it's very far away. So there's something called the escape velocity, which you may have heard, and it's about 11 kilometers per second for the Earth. And if you fire something away from the Earth at 11 kilometers per second, it will never come back. Anything less than 11 kilometers per second, neglecting the fact that there's other objects in the universe that could attract it, it will come back. If you shoot it at exactly the escape velocity of the Earth, an infinite amount of time later, it will have stopped. But it will never stop moving away. So it has escaped. And if you shoot it at a velocity greater than escape velocity, it's just gonna keep going away from Earth. But what that implies is that I'm asking here, for example, how far do I have to drop something to get 50 meters per second? And it says I have to drop it from like 125 meters off the ground. But what if I wanted to get something moving at 12 kilometers per second, as in greater than the escape velocity of the Earth? Well, that's impossible, which means that this shape cannot be a parabola. And if we zoom out, we find these lines where x is approximately the escape velocity, and it basically says that if you want to drop something such that its speed is greater than the escape velocity of the Earth by the time it reaches Earth, well, that's impossible. So it says you have to drop it from a negative distance. It just doesn't make any sense. It's a bit nonsense. But as you can see, this blue function is not, in fact, a parabola. It just looks like one. Because when you're close to the Earth, gravity doesn't change much. It's pretty much constant. It's 9.81 meters per second squared. So it looks like a parabola, but it's not. Dropping physics, that's what that is. This one is also quite involved, maybe even more. It's not showing anything. Oh yeah, I have to show it. Get rid of this one. Show this one and this one. Mostly this one. Let's start with this. It's a normal distribution. It's a probability density function for any variable. So for example, I actually started thinking about this just because I was wondering about male height, for example. Across the world, you can get a mean. The mean is sort of like the center of this bulge, and S is the standard deviation. So a more spread out, a bigger standard deviation means that the values are more spread out, as in, let's say, heights of males across the world, they vary a lot, or they only vary a little bit. They vary much less, they vary much more. And the mean is saying, in this case, that the average male is 7 centimeters tall, or whatever unit you're using. That would be a very small man. So yeah, that's kind of what a probability distribution is like. So I guess you could think of it as, what is the probability that somebody is 2 meters tall? Well, it's definitely more likely than the probability that somebody is 0 meters tall, and 4 as well is small. And as you get farther and farther away from the mean, you're less likely to find somebody with that height. So that's the normal distribution. And the thing is, though, you can't really ask the question, what is the probability that somebody's height is exactly 2? Because the probability that somebody's height is exactly 2 is 0, because it's too precise, and people's heights are not that precise. But what you can ask is, what is the probability that somebody's height lands in a certain range? Let's say from 1.5 meters tall to 2.5 meters tall. You can calculate the probability that somebody's height lies in that range. And the way you would do that is by integrating this red function from 1.5 to 2.5, which means that we have to integrate this nasty looking thing. Even without all these factors like M and S and all that business, integrating that can't be done or can't be written using elementary functions. You have to come up with a new function, which is just the integral of that. And because of all these factors, you have to play with that function. It's called the error function, and it's pretty much the integral of the Gaussian, okay? And here's what it looks like. It makes a lot of sense that it looks like that. Oh yeah, I forgot to mention another very important point. The volume, not the volume, I keep saying volume, the area under this curve has to be 1, because if basically, in order to do, like I said, what's the odds that somebody is any height, you have to do the integral from negative infinity to positive infinity of this red function. And the probability that somebody is any height is obviously 1. So the integral under this red function has to be 1. And for example, what's the integral you could do from 1.9 to, or sorry, yeah, 1.9 to 2.1, finding the area under that there would tell you the probability that somebody's height lies from 1.9 to 2 point. I'm using, it's at 1.8 and 2.2. Anyway, I already explained that. But basically the integral under the red function is 1, and that is sort of maintained. You have to use this square root of 2 pi factor here, but think about this S is the standard deviation. So as S is bigger, because of this is in the X kind of area, when S is bigger, it makes the function wider. See? But when S is bigger, it makes the function shorter. And because we do that in the same amount, we make it just as wide as we make it short, the volume is, or the area under the curve is maintained. So that's kind of neat. And as you can see, the integral of that function is this blue function, and it is 1. So basically, in order to calculate, let's say, the probability that somebody's height is anywhere from 1.8 meters to 2.2 meters, I'm just going to type it in here. I'm going to say integral, or actually not integral. We're going to use the p function. I'm going to say p of 2.2 minus p of 1.8, and this is the probability that somebody's height is in that range. And it says it's 38%. So basically the area under this curve from here to here is 38% of the total area under the red curve. So that's what's up. And here I just proved that this blue function using the error function is pretty much the integral of the red function, because I just do the numerical integration here using Desmos. And it's supposed to be from negative infinity to x, but you know, at negative 10, in fact, even if I use negative 1, it's pretty much 0. So adding up all these values is not only a waste of time, but it's impossible to go to negative infinity, so I use negative 10. But look, this function is the green one, and it's pretty much exactly the same as p of x. And as you can see, if I didn't go from negative 10, if I went from negative 1, it's still pretty much exactly the same curve. What if I went from like 1? It's still pretty much almost the exact same curve, but it would break once I get to like 2, for example, and it's way off. It's actually the right it's actually the right shape, but it's just shifted down, obviously, as you can see. Anyway, I thought that was kind of cool. So this is the error function. So if you ever want to calculate probabilities, that's your best friend right there. That's probably pretty great to use. I don't really need to show these. They're not that cool. This one, I think it's kind of cool. It's kind of nice. You basically have 2 gears meshing. And look, I even made it so that the gears somewhat mesh quite well. This would be a great demonstration for maybe high school students or whatever. Show them some gearing ratios. So you have the input speed, and if the gear A has 12 teeth and the gear B has 40 teeth, then maybe I should make it even 20. Look at that. Now when A makes 1 rotation, B only makes half a rotation. So that's how you get gearing ratios. I'm sure you guys already understand that quite well. If you don't, I don't know what you've been doing. You didn't drive. You don't ride a bike. You know how gears work, right? But a lot of people probably don't. This is the heat equation. Pretty neat. So that guy, Joseph Fourier, all those years ago, he came up with the Fourier transform and all that stuff. Not because he was working with sound waves and frequency analysis of light and all those other kind of waves that we think of. He saw it in a completely unexpected place, and I linked that from 3 Blue 1 Brown. Maybe it wasn't unexpected to him. But anyway, imagine we have a bar of metal, a one-dimensional bar of metal, and the temperature at each point in the bar of metal is graphed as the y value here. So here the temperature is almost 1, and here the temperature is less. So here it's hot and here it's cold. And what we expect to see is that each point, see if it's hot here and not hot here, then the hot parts will get less hot, the cold parts will get more hot, and it'll all kind of just average out and get smoothed out. We should expect a smoothed out shape. As time progresses, the heat should spread. And basically, I'll just show you what that looks like. So as you can see, it spreads out. The heat spreads out. The hot parts get less hot. The cold parts get less cold. And that is the heat equation. Very nice. And how did I do that? Well, basically, he realized that you could do it by just saying that it's kind of the curvature. The sharper the curvature is, as in there's a really hot part next to two cold parts, then that should get squashed, its temperature squashed faster. Likewise, the opposite direction, more sharply curved it is like this, then the temperature will rise faster. And since this red function is just the sum of a bunch of sinusoids, what we can do is attenuate the higher frequencies, which have a higher curvature, and make them smaller faster. So get rid of the high frequencies basically, and you get a smoothed out shape, which is kind of intuitive. So we get the smoothed out square wave. Likewise, we have the smoothed out triangle wave. And we can just play that back and fast forward like that. That's the heat equation. Basically, attenuate the high frequencies more than the low ones. That's what's up. Euler spiral. I heard about the Euler spiral. I thought it was real neat. And it's a wonderful shape. The curvature kind of goes one way, and then all of a sudden the curvature reverses. And obviously there's some integrals involved there. And I don't remember how the hell this thing works, but I had the feeling I wanted to line them up like that. So I made many copies of the Euler spiral. So I made these cool waves, kind of like water waves. Very beautiful. What does it mean? Nothing. This I thought was kind of interesting. In a mythology video I was watching, he said that you can't, okay, first off, this is the parametric form of an ellipse. A is the width and B is the height, I guess you could say. It's the two dimensions anyway. So what is interesting is that if A is equal to B, obviously it's a circle, and as we can imagine, the perimeter of that circle is 3 squared times pi, so 9 pi. But you can write that down, right? You can write down 9 pi, but you can't write the perimeter of an ellipse in closed form or as using elementary functions. You can calculate it numerically, but this is sort of a demonstration of that. I'm calculating it numerically here. So let's take a look at this. A is 1, B is 1, so we have a circle, the unit circle. And what I did was I divided the perimeter of whatever it was by 2 pi, so that the result should say 1. So that's one circle, unit circle's perimeter. You'd expect maybe if you turn up A by a factor of 2, then the perimeter will go up by a factor of 2, but it does not. It only goes up by a little over 50%. And yeah, mythologists just claimed, and it's not a claim, I think it's true, but yeah, you simply can't write this down in closed form, like without the integration thing. You have to compute it numerically. This is the perimeter of the ellipse divided by 2 pi. So that is that. Ellipse perimeter. I'm trying to get this over with quick because I made this video already. Very sad, but there was no cursor, so you couldn't see what I was doing. So I have to re-record it. You know, pity me. Anyway, this is, imagine this is a map of the Earth, and we have latitude and longitude. So this would be, the bottom line would be the South Pole at -90 degrees, and the top line would be the North Pole at 90 degrees. And then we have -180 to +180 around the equator. And basically you can write your coordinates wherever you are on Earth. Let's look at, I'm in Ottawa. Ottawa coordinates. Check this out. We have about 45 degrees north, 75 degrees west. So let's do that. We'll say that this is 45 and what was it? 75 west. So I'll just put -75 there. And then let's put in Tokyo coordinates. See how it knows what I was about to type? Pretty sketchy, Google. Come on, guys. I'm gonna round that to 36 degrees north. So we'll put in 36 and then 139. Let's just say 140. What? I think I got my, man, I think I got them mixed up. A and B? Who the hell wrote this shit? A and B. A is the X. Oh man, I did mess them up. It's 45 north. B is the Y. Oh man. This should be 45. And it should be here -75. I knew it looked wrong. God damn you. So there's Ottawa on the map. And let's add Tokyo. Anyway, this is supposed to be a distance calculator. It's going to tell me the distance from Ottawa to Tokyo. 35 degrees north and 140. So 35 degrees north, 36 it was. And that's 140 east, is it? Yeah, 140 east. So we'll use positive for east and negative for west. So if you look at the map of the world, and that's -180. Anyway, that's Ottawa, and that's Japan. And here it has the distance from Ottawa to Japan. Wow, 10,000 kilometers. Look at that. Distance from Ottawa to Tokyo. 10,317. Look at that. 10,317. It's pretty much exactly correct. Pretty great. Distance calculator. It's actually not too challenging to do that. Basically, you convert it to like spherical coordinates, and you get the latitude and longitude and convert them to actual positions in 3D space. And then I had to figure out, using that straight line distance, what's the arc distance. So if you were to fly a plane from Ottawa to Tokyo, how long that would take. Anyway, it's a little bit of math, but it's kind of neat. Kind of cool stuff. I like that. This one's a great demo of just math facts. It's a bunch of ways of making the same curve. And I thought that was kind of amazing because I didn't know. So 1 over x, famous curve, we all know it. We have the square root of x squared plus 1, less famous curve. This function, you can come up with a sort of understanding of what this function is. Imagine you are moving along the line at y is equal to 1, this line here. And you want to see what is your distance to the origin as a function of your x position along this line, that would be this blue line. So basically, once you're far away, it's pretty much linear. You know, you go one step out here, you go one step further from the origin. But here, you never actually get to 0. Here, the distance is 1. So that's that function. We also have this one, which I'm not going to try and describe that. We also have the hyperbolic sine and cos functions. We can write it using parametric form, and we get kind of the opposite of this one, the negative version of it. That's kind of cool. And then we have basically these two equations written in implicit form. X squared minus y squared is equal to 1. And the same way this equation, imagine this is a plus sign, that's a sphere, a circle. And imagine you get rid of the h's, that's a circle. So the hyperbolic sign is to this equation what the normal sign is to a circle. That's sort of why they call it the hyperbolic sign, because instead of a circle, it's a hyperbola. I actually don't know anything about hyperbola. I just thought that was kind of cool. This is a shoelace integral. I wish I could kind of explain how it worked, but I forgot. But I can tell you what it does. Basically, it tells you what the area is enclosed by this black curve here. And it says the area is 3.18, but who cares because it's an arbitrary curve. But we have that. It's the area of that. And the way it works basically is it's doing integration. It's summing up the area of all the little triangles. Imagine you get a triangle, a very long skinny triangle, from the origin to 2 points on this curve. Draw a triangle like that. And add then another triangle like that, and then add then another triangle like that. Anyway, you add up all those little slivers of triangles, and you do that for the whole 2 pi way around, and you get your result. This is not 2 pi, that's 2 pi. And that is the area enclosed by this curve. And if you make it instead just like pi, you get half the area because it's only doing the triangles from here to here. So that's what that is. This, I'm quite proud of this. I made this a while ago. Obviously, I don't know how long ago. But we have a parametric curve, and I was curious, how can we quantify the curvature at any point on this curve? And basically, I graphed it. I did the math. I did my math using my intuition, and I came up with this black line, which is proportional to the curvature at any given point on that line. And I also made it perpendicular to the curve. And basically, yeah, this was my own kind of intuition based on what is the curvature at a certain point. And it is pretty much the reciprocal of the actual definition of curvature, which involves using the radius. So if you have a curve and you get the biggest circle that you can get tangent to that curve, tells you about the curvature of that. Obviously, the bigger the circle is, the bigger the radius is, the less it's curved. The smaller circle, 1 over the radius, has a higher curvature. And so basically this black line's length is 1 over that radius. And the way I came up with it was quite complicated, but as you can see, this is a pretty good representation of the curvature of that green function. And let's see if I can change like a value here. Where is the green defined? X, t, and 3 and 4. So I can make it like more gentle curve, and it still tells you the curvature at every point on that parametric curve. Pretty amazing, pretty beautiful, pretty advanced stuff. I don't know what the hell I was thinking how I made that, but I did, and it works. I actually made these for my astronomy class, and it's a bit involved to explain what's kind of going on here. But imagine you are the Earth and you orbit the sun along this red circle, and this green planet here is Mars. And you basically, as you go around this circle, it takes a whole year for you to go around that circle. You're also spinning around. You know, it only takes 24 hours for the thing to spin around. But basically, if you're looking at Mars in the sky, it doesn't move because it's very slow. But what you can do is look at the position of Mars against the stars in the sky every day and keep track of how Mars moves against the stars every day. And that's all you could do back in the day, because we had no idea what the structure of our solar system was. Maybe some people did. But anyway, this is what you get. So think about the position that Mars is on the sky is where this purple line intersects with the celestial sphere, the stars, which should be an infinite distance away, but I made it a finite distance so you can look at it. And as time progresses, we go around, and each day we measure Mars's position with respect to the celestial sphere, and we see that it has moved as the days progress, and it's always moving counterclockwise. Okay. But then watch this. All of a sudden, it starts to move clockwise. See how the intersection of the purple thing flips directions? See, it's going counterclockwise. Now it's going clockwise, and then it keeps going back in the counterclockwise direction. And that is when Mars is in retrograde. So basically, as we pass by Mars, it appears to reverse direction in the sky. And that really confused astronomers back in the day. They were like, because normally you don't expect something to be like in the middle of space for no good reason. But that's because they were thinking about things from their geocentric perspective, when really it is a heliocentric world. As far as I'm concerned, we're going around the sun. And basically, this is the old system, the Ptolemaic system. This is how they described the position of Mars in the sky. So here we are, we're in the middle, the geocentric universe, and the path that Mars takes is this blue line. You can see that purple dot would be Mars moving around this ridiculous shape made using epicycles, which is just circles on circles. You can actually see we have the red circle and the blue circle. So the red circle, the blue circle on the red circle, sort of as you go around both of those. See how we're going around the blue circle? We're also going around the red circle. We get that curve. That's called an epicycle. And this was their way of modeling how Mars reversed directions in the middle of the sky for no particular reason. And the scientific method has determined that this is not as good as the Copernican retrograde motion, the Copernican model, the heliocentric model. I'm gonna shut up. DTFT, this one's great. So I made it animated just for fun, using the wave equation. The wave equation is pretty neat. I don't know if I can get into that, but basically, remember I showed you the heat equation. Wave equation says that you have a wave, and it just says that the acceleration or the force that a point on that wave should experience is proportional or negatively proportional to the curvature at that point. So if it's curved like this a lot, then the wave equation says that it should get pushed up a lot. If it's like this, it's flat, there's no curvature, it just carries through with its momentum, there's no force on it. But once the curvature reaches this point, then it's getting pushed down a lot too, and it'll slow down. And basically the wave equation says that a wave should go like this. Pretty straightforward stuff. And what this is not to do with that exactly, but basically it is summing together 4 or 5 different sine waves so that they pass through any 4 points. They're equally spaced, but there's the any 4 points, and there's the orange function passes through them. And if you apply the wave equation, you make, basically it just means that the wave equation, like I said, higher frequency waves have a higher curvature, so the higher frequency waves should go up and down faster, and the low frequency waves will go slow. So that the waves, this would be a slow big wave, and the little high frequency waves will be going up and down much faster, slowly and faster, higher frequency. That's what's up there. That's the discrete time Fourier transform. That's what that stands for, DTFT. Look it up. Pretty neat stuff. But you can do it in Desmos with a little elbow grease. There was no elbow grease involved in making that. This is a Maclaurin. Who's Maclaurin? Taylor series? Not the same as Maclaurin. I think it's pretty similar though. I was just thinking about how would I approximate the sine function on a computer? You see, because the Maclaurin series will get you an approximation of the sine wave at 0, for example. Look at this. I'm going to get rid of this one. So here's our approximation of the sine function at 0. And if we increase m, it does spread out. But still, at the end of the day, if I want to figure out what sine of 30 is, I should be able to do that without having to add on a billion m. Okay? So what I do is I use the mod function, modulo, basically saying 30, well, that's the same thing. You can go 2 pi many times over on the left and should get the same value. So that's that. So if we get rid of this, what's interesting is there's no sine function anywhere here. There is a factorial, so that's probably not too cheap to compute. But we're able to start with that. And by turning up m, we get gradually closer to a sine wave. Very nice. Sine Maclaurin. That's it. Spiral car, cute spirals. These ones really are pretty cute. Maybe we could change the value slowly. Play it. Play it forward. Oh god, it's like the slower you change it, the worse it is. I should go from 0. Oh, it's just when it's very close to 0, it changes very fast. Look at that, beautiful. Wow, do you see that shape there? When it kind of coincides, it looks really great. Bam. So that's what's up. That's cute spirals. I agree, they're quite cute. I came up with the name myself. This, I think, is a very important graph, which I'd like to show you. And basically, it has to do with the phase of a sinusoid. So we have sine and we have cosine. But what if we want a sinusoid with a phase somewhere in between there? One way we could do it is pretty straightforward. We can alter the phase like this. See how I change t and it goes left and right? That's pretty straightforward elementary function stuff, okay? But what if I added different amounts of sine and cosine? So let's put this at 0. We're going to put t to 0. Okay, what does that mean? So we have a cos function, the purple one, and sine of 0 is 0. So we have no cos function. The amplitude of that cos function is 0. And here we have cos of 0, which is 1. So it says we have 1 sine function and 0 cos function. So that's our sine wave with a function of 0. With a, what the hell, with a phase of 0. Anyway, what if we increase the value of t a little bit? Just a little bit. Okay. So now sine is sine of this is a little bit negative, so we have negative cos function, just a little bit of cos, and still a lot of sine. And what I'm going to do is I'm going to call this one f of x. I'm sweating in my room here because I closed the door so you don't hear the fan out there. Oh my god. When you close the door in the winter, it gets hot in here. Anyway, that's enough about me. F x plus g of x. So what happens if we add basically different amounts of cos and sine together? What do we get? We get this function. It's another sinusoid of the same frequency, but with a different phase. Check it out. As we add more or less of the sine function and the cos function. Look at, basically this black one is the sum of the red and the purple function. So we can add more or less of cos or sine function and get different phases. And this is very important for doing Fourier analysis on a function. So look at that. I mean, I don't know what I can say about it. But basically you kind of go around in a circle. You add, you know, a lot of cos, no cos, negative cos. You add different amounts of sine and cos and you can get any phase. That's the idea. And basically see f of x plus g of x is equal to this. See how they coincide? They are the same. Anyway, that's what that is, combinations. I thought that was very important mathematical fact for doing Fourier analysis. Here we have the Cantor function. This is interesting. So there's basically a theorem in calculus which says that in order to go from 0 to 1, your slope has to, somewhere between 0 and 1, your slope has to be positive at some point, right? Obviously. But what Georg Cantor came up with the function that violates that theorem, and this is how he did it. It's a bit of an odd function. I guess it's because it uses that infinite thing. Same thing as like a Weierstrass function, which I graphed before too. But look at this. A Weierstrass function, it kind of violates a different thing. A Weierstrass function has historically served the role of a pathological function, being the first published example, 1872, specifically concocted to challenge the notion that every continuous function is differentiable except on a set of isolated points. So it is a continuous function, but it's not differentiable anywhere because it uses like really tiny little sine waves that make it rough. So it's not differentiable anywhere. So he used that to challenge that notion. Cantor did something similar with another theorem, which is this. So basically, and this actually has to go from -1. It's a bit odd, my indexing. Okay, so here's how you construct the function. You may have already seen it or figured it out, but basically you break up this interval from 0 to 1 into thirds, and at this point, when n is equal to -1, we have 1/3 of the function has a derivative of 0, has a 0 slope, and 2/3 of it has a positive slope. And what we're going to do is we're going to recursively, we're going to get these sections with a positive slope and make 1/3 of it flat. So right now we have 2/3 of the function is positive slope, has a positive slope. Now 2/3 of that is now 0. So we have 2/3 times 2/3 of the function has a positive slope. And then we have 2/3 of 2/3 of 2/3. Basically 2/3 to the power of 3 at this point. So let's do that. I'm just going to add 2 to the n. We'll do 2 over 3. Ooh. To the power. Ooh. To the power of n plus. Ooh. N plus 2. Check this out. So here it says 66% of it is sloped up. Now less of it is sloped up, more of it is flat. Less of it is sloped up, and you continually multiply something by 2/3, you will eventually reach 0 once you've done it an infinite amount of times. So you ramp this number up to infinity, and what we get is almost none of the function has a non-zero slope, which means that all of the function has a slope of 0, and yet it still goes from 0 to 1. Obviously n is finite in this case, so there's still little tiny sections which are sloped up, but they only amount to 0.07 of the whole thing. And if you did ramp that n up, then none of the function would have a positive slope. It would all be negative, and that is the Cantor function. Very cool. I'm done with that. Then we have this one, was just me playing around. It's kind of fun. You got a square. Boom, boom, boom. What's going on? Don't ask. Moire pattern, demonstration of the Moire pattern. It's like an interference pattern between waves. But it happens, you see it everywhere. So basically we've got this red set of lines. This is the distance between those lines. And then what we get is this is the interference pattern. See, just by changing the distance between there, we can change the angle of the interference pattern. Pretty neat. Or we can just change the angle of the actual red lines. Very cool. That's a Moire pattern. That's what that is. Then we have parametricception. This is like functionception, except instead of a function on a function, it's a parametric equation on a parametric equation. And I never wrote it down. It's just like this. X of t, y of t, where this is 2 pi. So we have this red parametric equation, whatever you want to call it. And then we have another one using x1 and y of 1. So x1 of t, y1 of t. And we have basically a big lemniscate and a baby lemniscate. Now the question is, if you were to graph, this is traced out like in this shape. With t varying, you trace out this path. And the origin is here. But what if, while tracing out this blue curve, you were moving along the red curve, and you went like that, and you changed the orientation of your grid so that it aligned with the sort of direction of the red curve. Kind of hard to describe what I was thinking, but you can kind of see what I was thinking when you see the actual result right there, which is a figure 8 and actually follows the curve really well, exactly how it's supposed to. So you could put this figure 8 shape on any curve you want. In this case, it's x and y, blah blah blah. We could do it so that the x is just x, and now it's just a sine wave. And then we'll make this I don't know why I made the frequency times 2. Ugh. Yeah, anyway, you get the idea. My first lemniscate. Oh, I'm done the video. Thank goodness. I was getting hot in here. Thanks for watching, guys. That's everything I made on Desmos, especially if you include the first video. Thanks for watching, and have a good one. Peace out.